Hello and welcome to our first video on energy equations. In this video we're going to have a brief recap of energy stores and pathways and looking at how we can use energy descriptions, but we will quickly move on to the main energy equations that your students are likely to find in their exam specifications. In the next two videos David Richardson is going to introduce you to thermal energy concepts and the calculations and practicals that you're likely to find in exam specifications again. And in the last video, David, Rachel and I will look at further concepts on energy equations and really suggest some good activities and contexts that you can use to engage your students in understanding energy equations and how to use them in calculations of real problems. So here is a mind map that will help us to recap some ideas from your previous videos. Now, first of all, energy is always conserved. It is a numerical quantity and not a physical quantity in the usual sense of the term. So it's not something tangible that you can feel and touch and so on. But as a numerical quantity, it allows us to make accurate calculations that predict what might be possible and what is impossible to happen. And lastly, energy does not have causal powers. What does that mean? How can we get our students to understand this idea? Well, let's give a very simple example. I could be holding this ping pong ball in my hand, and you would agree, and hopefully the teachers you're working with would agree that at this particular height there is a certain energy in the gravity store associated with this ping pong ball. And the reason there is this energy in the store is because the ball has been raised to a certain height. But let's imagine that I'm going to remove my hand. At that instant, when I remove my hand from underneath the ball, what happens to that energy? Is there any difference in the energy in the gravity store? Take a second to think about this. Well, obviously, there isn't any difference. There is exactly the same energy in the store, the gravity store, whether I'm holding it or whether I'm letting go of my hand. So in order to explain why the ball will fall when I remove my hand, I cannot really use an energy explanation. The only way I can describe and explain what happens is if I involve forces. So there will be an unbalanced force when I remove my hand that causes the ping pong ball to fall, because the support force is being removed. So the only force that is applied on the tennis ball or the ping pong ball is the gravity, the weight of the ball. You might have been introduced to the energy stores, and these are where there is a change in the system. What happens is that one store will be filled as one or more stores will be emptying. And these are the 8 energy stores that are introduced usually by the Institute of Physics. But in these 3 videos of calculations about energy, we will focus mostly on elastic store, the chemical store, the gravity store, the kinetic store, and the thermal store, because those are the stores where typically calculations are involved in terms of the examinations your students will take. So when we talk about energy transfers, we want to choose the change in the system that we are identifying or want to study. And then we define the start and end points of that change. And we can see those start and end points as snapshots in time. And once we've got those start and end points, we can identify the stores that are involved or associated to those end and start points. But it's also important to remind the students that in any energy transfer, there is always dissipation of energy, which means that that missing energy that we can't account for actually is not destroyed or disappears. It's being stored in the thermal store of the surroundings and as internal energy often of the system itself. Lastly, we looked at the pathways, which is that concept of energy in transit. So as it is energy in transit, it is not stored in a pathway, and that's why we look at pathways as the concept of power, which is measured in watts, and it is the rate of transfer of energy. So how much energy is transferred by the system every second. Now, these pathways are the conduit, if you want, that allows this energy shifting from one store that is emptying into a store that is filling. Now, the pathways that we recommend using are pathways by heating, and this can happen by particles, heating by particles, or heating by radiation, and two pathways of working pathways, so electrical working and mechanical working. So these are some general ideas of how we can use energy concepts to describe changes in a system. This is a useful graphic organizer that you can use with your teachers in introducing them to the energy calculations that they will most use in their 14 to 16 curricula. And we could start from the work done. Now work done, as you will know, is defined as a force timed by the distance moved in the direction of the force. That is measured in joules, and with the idea of work done, what is very important is that teachers understand that work done equals the energy transferred in the system. So if we want to give an example, a crane lifting a load, the work done in doing that will be the weight of the load that is being lifted multiplied by the height at which the load has been lifted. This links quite well with gravitational potential energy equation, because that is a calculation that describes the energy shifted when an object is raised to a certain height, or rather where there has been a change in the height of the object. And the kinetic energy equation is a way to calculate the energy shifted due to the movement of an object, and that is described by half mv squared. And if we go back to our example of a falling object, we could calculate quite precisely the mass of this cube, for example, and we can therefore calculate the energy in the gravity store, because that is mgh, and we could then let drop this object, and we could decide that our endpoint is the moment just before the cube is about to hit the floor or the table. At that point, the energy in the gravity store will have all shifted to the kinetic store, and there is a calculation that we could use there, which is half mv squared, which allows us to predict very accurately the velocity of the object at its lowest point. And we could quite legitimately assume that all the energy in the gravity store from the start is shifted to the kinetic store at the end point, because the energy shifted to the thermal store in this fall is going to be minimal. The air resistance on this object is not going to have a huge effect on the transfer of energy. So we could make that calculation and that prediction of the velocity of this object quite precisely. And lastly, we did talk about power briefly, and we said that power is always involved in the energy pathways, and power is the rate of energy transferred, so the energy transferred every second. Now, power is therefore also equal to the work done divided by the time taken, or the energy transferred divided by the time taken. Efficiency is another important aspect of this part of the curriculum, and we know that every time there is a change in the system, energy will be dissipated, and that is due mostly to mechanical processes that would cause frictional forces and therefore heating by radiation or by particles. Now, because it is a ratio, what's interesting about efficiency it is that it is unitless, and we have a calculation that we can use for efficiency, and that would be defined in different ways depending on what exam board the teachers you work with use, and that is useful energy transferred divided by the total energy supplied. Now, what I think is really valuable at this point when you talk about efficiency is to talk about the other ideas within the other science curricula subjects that link with similar calculations or ratios. For example, in chemistry, the yield of a chemical equation, and you could perhaps think in biology the limiting factors of photosynthesis. So that's very valuable, I think, to make those links and make them visible to your students. A really good way to show the efficiency equation in action is to look at a bouncing ball. So we could have a ping pong ball and drop it from a certain height and measure the height of bounce. Now, of course, we can do this very well with an app called Vernier Physics. Vernier Physics allows you to take a video of a moving object and to map where that object's position is on the screen frame by frame. So this is one I took earlier, and as you can see, we've mapped where the ball is at any one point. And the really nice thing is that Vernier Video Physics allows you to show the y versus time graph, but not only that, it also gives you the velocity time graph. So for example, we can see that the drop height was 93 centimeters and the first bounce was at 30 centimeters. So applying the efficiency equation with mass and gravitational field constant cancelling each other, is simple to see that 30 centimeters divided by 93 centimeters gives you a efficiency of roughly 32%. What is quite nice about having the displacement time and velocity time graphs on top of each other is that you can show your students and your teachers how the energy shifts from one store to another in the fall and in the bounces. So for example, in this first blue band here, you can see that the ball was held at the same height, so the gravity store is filled and the kinetic store, because the ball is not moving, is empty. But as the ball is starting to drop, then the gravity store, as you can see, the position of the ball decreases, so the gravity store empties, whilst the kinetic store increases as the velocity of the ball increases. In this little green band here, something quite interesting happens, because you have that the ball changes direction very suddenly, and it decelerates very quickly, and also it accelerates upward again. That is where the elastic store is filling, and initially the kinetic store empties as the ball reaches zero velocity, and then it fills again as the elastic store empties when the ball regains its shape. And in the last bit, where the ball is actually going to the air, you have that the kinetic store now decreases as the velocity is reducing, and the gravity store increases or fills as the position of the ball rises to the highest point of the bounce. So the gravity store at the end is full again, the kinetic store is empty because we got zero velocity here at the top, but you can clearly see that the gravity store now has a lot less energy than what we started with, and so that is where that missing energy is gone. We need to account for that, and obviously that has gone into the thermal store of the ball, of the surroundings, of the floor, and that simply increases the temperature of the ball and the floor and surroundings. So that's your energy transfers. I hope you enjoyed this first part of our video, and I'll hand you over to David now, who's going to show you some really cool stuff.